Welcome back to another class. We are going to continue on our discussion of global warming. I guess this is our third unit in air pollution and our final unit in air pollution, after which we can move on from gases to other lovely things like liquids. And we're going to be talking about water quite a bit. And we also have several other units that we'll deal with after water, time permitting. If chat people can let me know if the sound is bad or anything like that, I can maybe do something about it. Just a reminder that today is the due date for assignment 1, which hopefully you are aware of. And I checked it on Tuesday. I think I already had about 150 submissions, so I think people were sort of well on the way getting that thing in. That's all I really have to say. I mean, obviously I have a lot to say about chemistry and about this course, but in terms of like housekeeping stuff before then, I think we're okay. We don't really have anything due after today for a while, except I guess we do have unit assignment due, I think, Tuesday for the previous unit. And we might finish this unit today, in which case next Thursday we'll have another unit assignment due. So these kind of get due regularly, as you might be aware. But like I always say, if you do them as we go, there should be no problem. I don't know why this went off, but we'll get it back on there in a second. It's blinking, the light's on, so we should be good to go in just a minute. It's funny that I just looked around and thought, there we go, look at it slowly fade back to light here. This is where we left off. We were talking about last class evidence for the fact that our climate appears to be changing and has been for the last few decades, I guess I would say. And we had a few questions, and one of the things we were looking at was the impact of ice. You know, we talked about how ice seems to be melting all over the place at the caps, the North Pole, and in glaciers, which are either in typically northern areas or in places of high elevation. Talked about that too. Places like, you know, Argentina and things like that. And we kind of finished off, one of the last things that we were talking about was water levels and how sea level rise is a consequence of climate change. So I want to talk just a little bit more about that. And, you know, it seems maybe obvious that if you melt ice, it turns into water, and the water will flow into the oceans, and the oceans will then fill up, and ocean levels will rise. And while that certainly is an element of this, it's actually not the most important reason why the sea levels are rising. It turns out with water, the density of water, which is really how much volume a given mass of water will take up, it depends on its temperature. Like a lot of things, if you heat water up, it expands. It takes up more space, takes up more volume. It turns out water is at its most dense when it's 4 degrees Celsius, and that's the temperature you see in the fridge. And so if you took water out of the fridge in a glass and then you just left it on the counter and let it warm up to room temperature, what you'd find is the volume of water would increase a little bit as it warmed up. Just changes its density. So this is what we call the thermocline. It's the temperature of the ocean as you go deeper and deeper. Not surprisingly, it's warmest right close to the surface. And this is just one part of the world. I don't know where this was taken. Clearly not here, because the surface temperature of our water is not 22 degrees Celsius. But as you go deeper and deeper and deeper, the temperature gets lower and lower and gets closer and closer to 0 degrees Celsius. The average ocean surface temperature across the entire globe is 17 degrees Celsius. It's kind of a ripoff when you think about like where we are. I mean, I know we're in the north and so on, but like the water is not very warm here for swimming. So it can vary from about 2 degrees Celsius on average throughout the year to about plus 36 which maybe sound a little too warm, not that refreshing, I guess. So if the average is 17, what happens with climate change is if more energy is absorbed by the oceans and the oceans warm up, on average, warmer than 17 degrees Celsius, that'll cause them to expand, and they'll take up more space for that reason alone, given the same amount of water, right? Just the temperature will determine how much it will take up. So there's really kind of two pieces here. There is sea level rise due to melting ice, and there is sea level rise due to thermal expansion of just the water, just a property of water as you warm it up. So what does that mean for us? Is that what the world's going to look like? You know, this is a doomsday kind of prediction of a city being really underwater here. Does anyone know what this is from? Probably, this is obscure. We're getting obscure now. This is, I think, a still from a movie called AI. Anyone ever see AI? It came out like around 20 years ago, I think. I think it was a Steven Spielberg. Actually, no, this was the weird story of this movie. It was Stanley Kubrick was the director, and he was known for like really kind of weird, dystopian, you know, these sorts of movies. And Spielberg is known for like blockbuster, family-friendly, you know, like E.T. is Spielberg and this sort of thing. Stanley Kubrick was working on this movie, and then halfway through, I think he died while this was being produced, and Spielberg stepped in and finished it for him. And the mood of this movie like changes halfway through, from like really kind of dark and dystopian to like it changed and had a happy ending added in. Anyway, it's set like way in the future when New York is underwater. So this is obviously science fiction. This is not probably what we're going to see, but definitely sea levels could potentially rise, not to levels this high, but certainly to levels that would cause us a lot of trouble. For instance, there are some low-lying areas that are very much not above sea level too much at all. This is a place, it's a Pacific island called Nuku'oro Atoll, which seems to me like a really awesome place to visit, but it's like a ring that you can see, and it's got this lagoon in the center that is connected in one point, so water can kind of exchange a little bit in and out. And where it looks dark here, that's all like vegetation. So there's like a whole half of it there is just sort of like only beach all the way around. This is a place that it wouldn't take too much sea level rise, for example, just to submerge the whole thing. I don't know if there's any permanent population here, but like, you know, there are some low-lying areas that could be very susceptible. There was an article that was in National Geographic a couple of years ago, and what it shows is a map of the world and what it would look like if we had sort of worst-case scenario sea level rise. That means all ice all over the Earth melts, goes into the ocean, and I forget, there was a certain level of sea level rise that it would predict. And it predicted, I think, 7 meters was sort of the max that's possible under the worst case scenario. And then what they do is they take the map, and you can see the white outline here is the current borders and what it would look like if we raised the sea level by 7 meters. And, you know, like in the US, for example, much of the population is on the coast. So a lot of those places would be just submerged right underwater. If you look at where Florida is in particular, you know, Florida is pretty low-lying, and Florida would be essentially all underwater under this scenario. I've been to the top of the 2 tallest mountains in Florida. Does anyone know what the tallest mountain in Florida is? It's Mount Everest. Right? So you're looking at me like, Mount Everest is not in Florida, right? It's in like Nepal. No, at Disney, in Animal Kingdom, there's a ride called, I think it's what is it? Yeah, so that is an artificial mountain that was built by human beings, and you get to the top, and then it's a, you know, yeah, it's a ride at Disney. You know what the second tallest mountain is in Florida? Space Mountain, which is a different ride in a different Disney park. So that gives you an idea, really, of like how flat Florida is. It's a very, very, yeah, level place. So obviously, like, this would be disastrous for a lot of people. It would create untold millions or billions of refugees that would be leaving these flooded areas and moving to other places. This is another part of the world. This is like in Asia, and you can see certainly areas. Do I have my pencil here somewhere? Certainly areas here, large parts of China would be totally submerged. These are very highly populated places, and this would force a lot of migration. It'd be bad. Another problem associated with climate change is the instances of storms, tropical storms and hurricanes. And the reason why this is an issue, well, obviously the reason it's an issue is because these cause a lot of destruction. But the reason why it's believed climate change may be increasing the frequency and number of these things is that how these things form and how they travel and propagate depends a lot on the ocean temperature. So if the surface of the ocean is warm and the hurricane sort of mass is moving over, they tend to build energy and speed up. And if it's cold, they tend to lose energy and slow down. That's why most hurricanes, when they hit Nova Scotia, by the time they get to us, they're kind of in cold water, and they're on their way down usually. And sometimes they go right across Nova Scotia and over to Newfoundland. By the time they get to Newfoundland, they're even weaker still. So of course, if ocean levels, if ocean temperatures get warmer, these are going to be, first of all, more frequent, second of all, stronger when they eventually make landfall. So there's some evidence, maybe not strong, but it may look like hurricanes are somewhat increasing, but it's certainly not dramatic, at least yet. This guy is a golden toad. This is the first species to have gone extinct as believed to be a function or result, direct result of climate change. So this is a toad that the way it reproduces is it lays eggs, and it's an amphibian, so it lays eggs in water, and those eggs hatch, and then they develop eventually into frogs. And the way they do this is there's like a certain time of year that they lay their eggs, and it's like right after kind of like a rainy season. And they don't like look for like a lake or a pond or something like that. They like lay their eggs in like leaves like that have water collected in them and things like this. And it turns out they believe because of climate change, the very small region they only live in Costa Rica in like a 5 square kilometer range, so the very, very limited range. It resulted in drier than normal conditions, which made it impossible for them to reproduce. Now, obviously, if you have a species that only lives within a 5 square kilometer region, it will be very susceptible to environmental change. But there's lots of other issues or possible issues around that as well. So like a few years ago, I was in Newfoundland in May. And just south of St. John's, a place called Bay Bulls. And what you can do is go out on little tours there. And depending on the time of year, you will always see puffins, I think, or usually you'll see puffins. You can see whales, and you can see icebergs. And when I was there in May, there was all kinds of puffins that you could see. And I think what they do is they time their migrations to match the migrations of certain types of fish, so that when the fish arrive, the puffins arrive, puffins can eat, and so on. It doesn't take too much of a mismatch in timing that if ocean currents start to change and the fish don't arrive until 2 weeks later or 2 weeks sooner, that could have devastating consequences down the line on the species that also time their migrations to show up when they show up. So it's a very complex, and complicated system that there's great potential for upheavals just based on changing the timing of certain events. All right, what are the what two factors are most responsible for sea level rise? Thermal expansion of and expansion due to absorbed CO2, melting ice and expansion due to absorbed CO2, thermal expansion of water and melting ice and water displacement by boats. So our correct answer here is this one. The water itself expanding. I think there's a word missing in A, isn't there? Anyway. It's those two things for sure. Where's 7.4? You're there, aren't you? Sorry about that. I can't give you 7.4. You're on your own with that one. Coral bleaching is another thing that we're hearing about lately. Coral, unlike many other marine organisms, have no capacity to swim away if it gets too warm or too cold for that matter. Fish can move into waters that are at the temperature that they want to be in. Coral's kind of stuck. And because of warming of certain areas, it causes death of corals, the coral organisms, and you get what's called bleaching, where you can see, these kind of white regions develop. And there's been famously a number of important coral bleaching events have happened in the last decade in places like Great Barrier Reef. This says Great Barrier Reef health outlook downgraded to very poor due to ocean warming, and that's just back in 2019. So I can tell you it didn't get any colder since then. All right, so there's a debate about this, I guess. There's a debate in the media. There's a debate about lots of things in the media that the same debate does not exist among scientists. And so I would say in the literature, scientifically, among climatologists, there's no debate about whether climate change is a real thing or not a real thing. Of course, this is more a political argument than it is a scientific argument. And there's a lot of people whose livelihood depends on the sort of activities that we know now are forcing climate change and global warming. So it's a complex political and social issue. Although if we just leave it go unchecked, there's going to be much more serious political upheavals as a result. So what is actually causing global warming? How do we know? Well, this is an old paper. This is 2003. That's like almost 20 years ago. And what they were doing was looking at all of the different possible explanations for climate change and doing modeling. And this is the problem with climate change is climate is a global phenomenon. It encompasses the entire world. There's not a single measurement that you can make that tells you what the whole world looks like. So it's an exercise in aggregating a whole bunch of different types of data, and it's using those with making certain assumptions to make predictions about what's going on in the future. So it's far from like a certain science. It's not like we know exactly what's going to happen in 5 years or 15 years or 100 years for sure. We have to extrapolate based on models. But these people did their best using data that they could get their hands on. And they looked at sources that could be either considered natural, and these would be things like maybe changes in the sun, like solar flares and things like that. It could be things like volcanic activity. It could be, any kind of natural thing that may affect climate. And things that are anthropogenic, which are human-caused changes. And they looked at, they sort of modeled what each effect would have on our global temperatures. And this is our observation, this black line. This is the temperature anomaly that we've observed in degrees Celsius going back to 1900. And that's 20 years ago, so it's probably still like here now, 20 years later. Okay, so what they found is that natural fluctuations are what you see here in the kind of red line. And the red line that you see here are changes due to human-caused factors. So very quickly, like a long time ago, people have sort of figured out what is driving climate change. It's been well known for quite a while. Remember the 3 steps of solving a global environmental issue, crisis like this? 1, identify the problem. 2, technological solution. 3, political will to force those solutions into being adopted. We're already well past 1. We know what the problem is. Okay, it's us. It's human activity, for sure. Climate scientists agree, 97%. And this is old. This is back in 2013. That number, 97%, has only increased. That's the percentage of climate scientists that say climate change is both happening and caused by human activity. Whereas if you went to the American public, only 41% would agree with that statement. Okay? So it's a huge mismatch between what the average person believes or thinks and what is known by the experts in the field. And this is not just when it comes to climate, it's when it comes to all sorts of things. And the problem is that these are the people that vote. And they vote people in who will, hopefully at least, enact policies that they want, that they support. You know, some people vote for people for other reasons other than their policies, but, you know, hopefully most people. So if most people don't believe that climate change is happening or that we can do anything about it or that it's caused by humans, of course they're going to elect leaders that think the same thing. And those leaders are going to fail to act. And that's why this third piece of the puzzle is such an important one. Okay? The experts know what's happening. They maybe know what the solutions are, but that's not enough. You need that third important piece. And I guess in a way, you know, I say political will, but really what political will is equal to, in my mind, is public awareness or public education. Because if the public doesn't know about something or doesn't believe in something, they're not going to elect people who are going to take it seriously. So when you think about that yourself, you know, we all have, I guess, an obligation to do our best to try to limit our effects on the climate and, you know, to keep things as good as possible. And we talk about little things we can do, like, you know, recycle, take your bike, this kind of stuff. But really, one of the most important things you can do is elect people who are going to force the big changes. Or elect people, or maybe not elect people, but send letters to politicians, advocate with politicians to make these sorts of changes. Because that's the weak part in this whole process right now when it comes to climate change, is the political part. This is the percent of Americans who believe the Earth's temperature has been increasing. Percentage who are extremely or very sure that this is the case. One thing that may give hope, at least, is that there seems to be an increase. This is from 2020. You know, it's increased from 43% in 2019 to 63% in 2020. So there's an increase in public acceptance of this reality, which is good, right? Because that needs to get high before politicians are going to make that a priority. Now, of course, the Americans that's just one country. You know, there's the entire globe. This is a global scale issue. And, you know, Canada has made this same thing. Like, Canada's like, why should we hurt our economy if we're only a drop in the bucket compared to all these other people that aren't doing anything? And that's always, like, Canada's always kind of had that stance, which is kind of a hard thing because you have to, you know, everybody really needs to work on this together. So what's actually going on from a chemistry point of view? Why am I talking about global warming so much when, like, I haven't even, this is a chemistry course. I haven't said anything yet about chemistry. Well, let's look at what happens. The reason why global warming happens to begin with, why certain gases cause global warming, like CO2 and methane and things like that, and others don't, like nitrogen and like oxygen. So what happens is, you know, we receive energy from the sun in the form of electromagnetic radiation. We say light, but we know only what, 40-something% is visible light. 50% was infrared light, and 8% was ultraviolet. That all comes to the Earth and is absorbed mostly by the surface of the planet, which causes the planet to warm up. And you feel this. You go outside on a sunny day, and it's hot. You step in the shade, it's less hot. That's just simply the energy from the sun that you're either absorbing or you're not, if you're in shade. So that causes the temperature of the surface of the Earth to increase. Then at nighttime, when the sun's on the opposite side, it cools off. What's actually happening is the Earth is radiating that energy, or some of that energy, back outwards from the surface of the planet just out into space. So this is the solar spectrum of our sun. It actually is how we know what the temperature of the sun is, because we know something that is a temperature of around 6,000 degrees Kelvin, that's degrees Celsius above absolute zero, would give a solar spectrum like the sun. It turns out every single object that has temperature is always giving off light. It's emitting light. Like our bodies right now are emitting light. But the amount of light and the color of light is dependent on the temperature of the body. So for something very hot like the sun, that is mostly visible infrared and ultraviolet. You get this one. If you cool it down by 1,000 degrees, you'll still get some visible light being put out, more infrared, less ultraviolet. Even something like 3,000 Kelvin is still giving off some visible light, mostly now in the red part of the spectrum, and mostly in the infrared. Now our body temperature in degrees Kelvin, it's like what, 37 degrees Celsius? That's 310 or so Kelvin. So compared to like the sun and compared to all these other temperatures you see on this, we're not very warm. We're cold. And so we're not giving off any light. Our bodies are not giving off any visible light. All of the light that our bodies are giving off is in the infrared range. Same thing with the planet. At night, when the sun goes down and the Earth is warm after a hot summer day, it's giving off light, but it's not giving off visible light. Like you're not looking at the ground and it's glowing and you can see that light with your eyes, but it is emitting infrared light that just goes out into space. And that's how the Earth cools itself off. It emits infrared light away from the Earth, absorbs light in from the sun. And if those two are balanced, the temperature of the Earth on average remains constant. All right. Jaden Smith says this: they want you to believe that the sun is hot. I urge you to ask yourself, have they ever touched it? Think about it. So yeah, no, we haven't touched it. The reason we know it's hot, though, is because of the wavelengths of light that come away from it. Similarly, we can figure out the temperature of stars that are like, thousands of light years away. But we can measure their temperature based on the wavelengths of light that are coming. So black body radiation is what we call this infrared light that is emitted by warm bodies. And we actually take advantage of this. If you look at like night vision goggles, the way they work is they detect infrared light, and objects that are warmer give off more infrared light. So you can kind of delete backgrounds and you can see images sort of like this, where objects that are warmer than the surroundings will appear to glow. Because we are, at room temperature, 15 degrees or so Celsius warmer than our surroundings. And so using infrared glasses, you can see them. You see the same sorts of things used sometimes by people who do like these house inspections. And they'll take these infrared photographs of houses, and what they show is areas where your house is leaking out hot air. And it can help you sort of insulate your house better and actually address the areas where most heat is being lost. So it's pretty useful. But if you make something hot enough, it will start to give off visible light. So this is lava, and you can see certainly reddish, orangish light that comes off that. Of course, this is at a much higher temperature, and so the spectrum that you see is maybe closer to this one, where you're starting to see some visible light that's emitted from this object as well. Same thing if you have one of these old-fashioned stoves. This is, I say old-fashioned. Mine is like this at home. My sister-in-law's dad spent most of his career as a repairman for, I don't know, Maytag or Kenmore or one of those companies. And he urged me not to get a glass top stove because he said 95% of his work in like the last 10 years was replacing the tops of those glass top stoves because they shatter. And sometimes they shatter just because of the heat. Sometimes they shatter, he said, because somebody reaches over the stove to pull a container out and a can comes down and smashes it. So he said, get these if you can. They're hard to find now, I think, but I do have one. Anyway, you turn them up to max and they look orange, reddish orange. And that's because they get to a high enough temperature that they start to give off some visible light as well. And if you get it hotter and hotter, what happens is that the color of the light that you see starts to change. So if you get it to a much higher temperature, it starts to look white. And then if you get it even hotter than white, it shifts it enough that it starts to even look blue. And so you can almost tell by the color of the light how hot the object is. So Yoda was right. Luminous beings are we. We are all giving off light at this moment. It's just not visible light. You need infrared glasses to see them. Makes me wonder, like, it would be kind of neat if you had infrared vision that you could like see in the infrared. Then like, it'd be useful if you were like a predator at night. And by predator, I mean like hunting for your food, not like the other kind of predator. You know, if an animal could see in the infrared and it could detect warm-blooded things in a background of blackness, it would be a lot easier for them to hunt. Here's a picture of bats flying through an infrared camera. For an object at body temperature, most black body radiation is emitted in what energy range? Infrared, ultraviolet, visible, or X-ray? And the answer is IR. So IR light is not light we can see with our eyes, but we can feel it. It makes us feel warm. It's not high enough energy to break bonds, but we can absorb it. So these are like those red lights. I think I talked about this before that used to hang in bathrooms. You could flick them on. Or the ones that you would hang over like a cage of freshly hatched chickens. Keep them warm. So the greenhouse effect basically is like radiation comes from the sun, just like this is an actual greenhouse. Radiation, visible light, goes right through the glass, and it warms up the objects inside after it's absorbed. And then after it's absorbed, those objects want to re-emit energy in the infrared part of the spectrum. And so the infrared comes out, but the infrared can't get through the glass. It gets absorbed by the glass gets warm, and then sends infrared light back in. And so this is how a greenhouse works. It lets all the visible light in, but it doesn't let all of the infrared light back out. So it causes the temperature to increase in there, and you have this hot environment for plants to grow in. Our Earth works the same way. Our atmosphere is transparent to visible light, and it lets all the visible light in from the sun. Then when it starts to give off this infrared light to cool itself off, some of that infrared light that's being given off gets trapped or absorbed by our atmosphere. And once it's absorbed by the atmosphere, it can then re-emit back down and be reabsorbed by the surface of the Earth. Okay? So that's the basic way that the Earth is, we have this greenhouse effect. In fact, you know, we have all kinds of gases in our atmosphere if humans never existed that would create this greenhouse effect. And if we didn't have this, if our atmosphere didn't have any greenhouse gases at all, and just had oxygen and nitrogen, which are not greenhouse gases, the average surface temperature of the Earth would be about 20 degrees lower than it is now. And that's pretty important because, you know, in Nova Scotia, what that would probably mean is we get like a couple months maybe above 0, 2 or 3. It would have been a lot harder for a lot of different types of organisms to get themselves established. So the greenhouse effect is actually good. It naturally increases the temperature of the planet by about 20 degrees, which puts the majority of the planet into a comfortable range where we could live. The problem is what we've been seeing over the last 100 years or so, which is what we call the enhanced greenhouse effect. And the enhanced greenhouse effect is like beyond the 20 degrees that's naturally already there. It's extra because of extra gases we're putting into the atmosphere due to human activity. And the most important of these is carbon dioxide gas. So why is CO2 different from O2 or N2 or any other gas that's in the atmosphere? Well, CO2 has covalent bonds between carbon and oxygen. And the way we often think about these bonds in chemistry is if they were like balls attached by springs. And these springs can either be compressed or stretched. And in an ordinary molecule floating around this room right now, those CO2s are sort of vibrating back and forth. And there's constant vibration of molecules at room temperature. There's lots of energy in there for these vibrations to happen. It turns out quantum mechanics dictates certain rules about how these things can vibrate. They can't just vibrate any which way it wants. There's only specific ways that are permitted. It's permitted physically to vibrate. And why? It's just fundamental rules of the universe. There's not really a good answer beyond that. And for carbon dioxide, the two most important of these are what's called a symmetric stretch, which looks like this, where you have the carbon in the middle, and then the two oxygens stretch together, and then come back together. Stretch, so they're like in perfect harmony. Okay, those two bonds are always identical, and that's called a symmetric stretch. The other one is called an asymmetric stretch, where one shrinks as the other grows. So it's almost like the two oxygens are fixed, and the carbon swings back and forth in the middle. And we call that the asymmetric stretch, because one is shrinking as the other is growing. So like this kind of movement, online people can't see me. Let me move this. So this way. This kind of stretching back and forth together is symmetric, and then asymmetric would be like this. Okay? So this is important for CO2, that it has these different stretches. It's got other types too. It's got these which are kind of called bends, which are kind of the bond kind of flexes back and forth like that. So what happens is these molecules can absorb different types of light. And it turns out for ultraviolet, we know molecules absorb UV light and it causes bonds to break. We know microwave, when things like water absorb microwave light, it causes the molecules to rotate around. For infrared light, what it does is it causes these vibrations to turn on. It causes the molecule to vibrate in specific ways. So that's what the energy is for infrared, and that's all it allows it to do. So I'm going to bring in another idea here, and this is the idea of polar bonds. Remember we talked about polar bonds before? I think we did, didn't we? Yeah. So it's when you have one atom in a bond that pulls the electrons close to itself so that the charge across those two atoms is not uniform. One's more negative and one's more positive. An example here is hydrogen fluoride, HF. I'm just rewatching Breaking Bad with my daughter, and they just got to the point, I guess it's episode 3, where he has a couple of bottles of HF and tries to dissolve a body with them, which sodium hydroxide would work better, I think. Not that I've put a lot of thought into that. So we have HF here, and we have an unequal sharing of charge. So we know the electronegativity of fluorine is super high. Oxygen is also quite high. That means that fluorine and oxygen really like to pull electrons towards themselves when they're in a covalent bond. So CO2 has these oxygens, and what happens is the oxygens pull electrons away from the carbon, so it develops like what we call a partial positive charge, and the two oxygens develop partial negative charges. And if you add them all up at 0, the molecule is neutral, but the charge is not distributed evenly. This was all Linus Pauling. He won 2 Nobel Prizes. One for his discovery of, one for his, not discovery, but more developing the theories of bonding in chemistry, in particular called valence bond theory. His second one was for a Peace Prize. He did this project, I think in the 1950s. Did I tell you about this one before? Where he collected children's teeth. He went around the US collecting children's teeth from different areas. Like, after they had fallen out naturally, he didn't pull them out of children. And he crushed the teeth up, and he analyzed them for the presence of different elements. And he found that the children's teeth had contained a bunch of radioactive elements that are not naturally found on Earth. And they're only formed on Earth in artificial nuclear explosions. And so what he was showing was that nuclear weapons tests were putting debris in the air that was ending up in the food chain and being incorporated into our skeletons. And it led directly to a ban in above ground nuclear weapon testing. So from that point on, all nuclear weapon testing had to be done underground to prevent these isotopes from just getting into the atmosphere. So that's what he won the Nobel Prize for. And yeah, these are the two of them. 62 and Peace Prize was 62. So I think he did his experimental work in the late 50s. All right, so what do we know? We know that bonds have unequal buildup of charge. Some atoms can have more negative charge than others in a molecule. And we know that these bonds vibrate in very specific, predictable ways. And that by absorbing infrared light, it can activate these different types of vibrations. So this says oxygen is much more electronegative than hydrogen, which causes the OH bonds in water to be polar. Polar just means unequal buildup of charge. What do we mean when we say oxygen is more electronegative? What we mean is that in the covalent bonds, oxygen pulls the electron pairs, the shared electron pairs, to itself more strongly than other elements do. I think of this situation almost like you're lying in bed with somebody and trying to sleep, and there's one blanket that's covering the two of you, and you wake up in the middle of the night to find that they have pulled all the blankets off of you, and they're all nice and cozy and warm, and you are not because you have no blanket. In a chemical bond, if you think about the two atoms as being like two people in bed, and the lone pair of electrons is like the blanket, the electronegative atom is like the blanket hog. It pulls the electrons, wraps itself in those negative charges, and develops a partial negative charge, where then the other atom that it's bonded to is sort of stripped bare. It doesn't have the negative charges, and it develops a partial positive charge. So in CO2, the oxygens do just that and causes the carbons to be partially positive charged. So the oxygen atom attracts the electrons in the covalent bonds more strongly than hydrogen. Now these individual bonds, because there's individual bond polar bonds, these create what we call a dipole. And a dipole is just any object that has a positive end and a negative end. Well, for things like carbon dioxide, these dipoles actually cancel each other out because there's one pointing towards one oxygen, another dipole pointing towards another oxygen. They're in opposite directions and equal magnitude. So overall, we would say a molecule like CO2 is not polar. It's a non-polar molecule. Because even though it has polar bonds, and even though it has electronegative atoms like oxygen, they cancel out, giving a non-polar molecule. So that's important. We're going to bring back now this idea of vibrations, in particular the symmetric and the asymmetric stretch. CO2 is nonpolar. Think about that stretching motion. We're going to stretch those both bonds symmetrically, and this is when it's like maximally stretched. It's still nonpolar. The bonds are the same length. Everything's the same about those two bonds, still in opposite directions. Then they come back in, they come back out. This molecule, during all parts of the symmetric stretch, the molecule is nonpolar. However, the asymmetric stretch, when one is short and one is long, that causes the overall molecule to become polar because those two dipoles no longer cancel out. So essentially, CO2, when it's doing this asymmetric stretch back and forth, it's going to be like polar one way, not polar, polar the other way, not polar, polar the other way. And it keeps, as it's vibrating, you have this electric field that's oscillating back and forth. And it turns out that oscillating electric field, if it matches the oscillating electric field of light, then it'll cause an absorption. So that's kind of complex. There's a lot kind of built into that. And maybe I'll try to say this as clearly as I can. If a molecule has a vibration that changes its dipole moment, if the dipole changes during the vibration, then it will absorb IR light. It'll absorb some wavelength of infrared light. If a molecule does not have bonds like that, it won't absorb infrared light. Okay? So if it absorbs infrared light, it's a greenhouse gas. All greenhouse gases have this feature that they have vibrations that change the polarity of the molecule. So think about our top 3 gases in our atmosphere. Nitrogen is number 1. Oxygen is number 2. Not helium, but argon is number 3. Nitrogen just has 2 atoms. It can stretch, it can go back and forth. It can stretch and stretch, and, you know. It can vibrate. That's all it can do. It's never polar. There's no point in the vibration of N2 that you can have a polar molecule. So N2 will not absorb infrared light. It's not a greenhouse gas. O2, same thing. Any diatomic molecule, any molecule that just has 2 atoms of the same thing, O2, F2, Cl2, I2, Br2, any of those can vibrate back and forth and back and forth, but at no point is there a dipole moment in any of them. Also, things like argon don't even have bonds. It's just a single atom. They can't absorb infrared light either because they don't even have any vibrations at all, because you need at least 1 bond to have a vibration. So the number 1 gas, no absorption. Oxygen, number 2, no absorption of infrared light. Argon, number 3, no absorption of infrared light. Then comes in good old number 4, which is CO2. CO2 does absorb infrared light, and it's the most abundant of the gases that do absorb infrared light, except for water. Water, depending on if the air is dry or not, also absorbs infrared light and is a greenhouse gas. But water is sort of in our, you know, it's an important part of our ecosystem, and we can't really not have water in our atmosphere. But CO2 is definitely an important one. This is showing a spectrum. It's a little bit complicated, but it's a spectrum, infrared spectrum of air, showing what gases absorb where. CO2 absorbs sort of a region of wavelengths that you see down here. Water absorbs out here and out here. A few other ones, methane, that must be a mistake because N4O is not a thing. Ozone absorbs a little bit there. And then there's some regions of the spectrum that nothing absorbs. It's in air. We call them windows because they're kind of blank. Nothing absorbs there. Cool. So why are pure noble gases like helium and argon not greenhouse gases? Well, they don't have any bonds. If you don't have any bonds, you can't absorb IR light. So these gases have no bonds and thus cannot have bond vibrations. All right. So we put a lot of CO2 out into the air. We have been systematically removing CO2 that's been locked underground in the form of coal, oil, natural gas, burning it, turning it into CO2, and releasing it into the atmosphere. So it just keeps going up. There is a process by which we can take carbon dioxide out of the cycle as well. It's sometimes called a biological pump. Does anyone recognize where that is? What's that? It's not Greenland. It is a country in Europe. It's Ireland. Yeah? St. Patrick's Day today. You should recognize Ireland. Yeah. I'm 75% Irish. So, yeah, Lukeman is an Irish name, actually. And my mom's maiden name was Mahoney, which is definitely Irish. And if you go to my parents' level, it was Lukeman, Mahoney, Ryan, which is definitely Irish too. And then there's a McGilvery, so there's some Scottish there as well. And what you see here is all this blue stuff in the ocean. And what that is a bloom of, what are these things called? They're like photosynthetic microorganisms that live in the water. Not algae. Maybe it's a kind of algae. I don't know. I'm not a biologist. I'm a chemist. But essentially what these are is organisms that live in the water, and they can bloom at certain times of the year, like huge population blooms as a result of maybe mixing of nutrient-rich cold water with warm water or whatever it is, ocean currents. And these organisms will live, they'll photosynthesize, they'll fix CO2 in the form of like carbohydrates and so on in their own bodies, and then they die. And most of them will just rot and turn CO2, which goes back in the air, but some of them will die and like sink to the bottom, the surface of the ocean floor. They can eventually get buried and covered up, and they can become, you know, in millions of years, deposits of things like natural gas in the future. But for now, it does take some CO2 out of the system. So there's some ways that CO2 does get fixed, but most of it stays in the atmosphere or dissolves into the oceans. This is atmospheric CO2 levels that have been measured regularly since before the 1960s. And notice the concentration in the air has gone from 320 to where it is now, which is maybe 410. So it's increased by about 35%, I would say, in the last 50, 60 years, which is pretty dramatic increase. I remember when I started teaching this course, I don't know when it was, like 2008 or something, it was down around here. And I remember like predicting to the class, like, you wait, you know, in like 3 years, we're gonna hit 400 parts per million, and that's gonna be big news. And it was like, we were like 385 or something, and this is so predictable. You can, like I can predict for you when it's gonna hit 450 and so on, assuming we don't make any major changes in the way we live. It does kind of oscillate up and down, so it is seasonal, right? Because during our summer, there's a lot more land mass in the northern hemisphere, and so when the trees start putting out leaves and growing and so on, that actually reduces the amount of CO2 in the atmosphere, only for it to decompose and go back into the atmosphere later. So it does oscillate depending on time of year, but there's this clear upward trend, which so far at least, no evidence that this is really stopping. Although there was the question last class about the pandemic, and did the pandemic cause a blip here? And I think I remember reading somewhere that it did, that it dipped, but then it like stormed back. Like, I forget. I'll have to find a graph for that and see if I can find it. So this is it. You can actually see it month by month. Like the data is publicly available. You can see it oscillate up and down and up and down. And so something that might be of interest if you want to keep an eye on it. We can actually go back and look at CO2 levels from a long time ago. The way we do this is we find a glacier that's been around for thousands of years, and you can take ice cores, you can take like a coring drill, and you can bring the ice cores up, and the ice has little air bubbles in it, and you can dissolve the ice, let the air bubbles release, and test the CO2 that's in those in those air bubbles. And what you can actually find is historic levels of CO2 going back in some cases hundreds of thousands of years. So we actually know quite well, not just our current CO2 levels in the atmosphere, but what the levels looked like at every point in our past. So this is what it looks like if you go back about 10,000 years. The levels historically are somewhere around there, which is like 260. And they go up and down a little bit. And then this is like, since we, developed gas engines, you know? Since the human population exploded from 1 billion to 7 billion in the last 100 years. So you can see there's a sudden, dramatic increase in CO2 levels. And you can see even where this stops. Like this stops at 360 or something. It's up here, like 410 now. We can go back even further. We can go back, this is at 400,000 years. And you can see that there are these cycles. It goes up and down and up and down and up and down. And we were kind of in an up to begin with. This is like the last 100 years. So this is what we've added since then. And the red line is the surface temperature in Antarctica. And what you can hopefully agree is that the surface temperature matches very closely the CO2 concentrations that were in the air. So we think that the amount of CO2 that's in the air is a major indicator of what the surface temperature is going to be. And it makes sense, since we understand the mechanism of how CO2 in the air absorbs infrared light, sends that energy back to the planet, and keeps us warmer than we would ordinarily be. All right, so this is CO2 concentration versus global temperature. In the last while, they've also matched very, very closely, not just historically, but in the recent past. So sources of CO2, an obvious one is driving gas-powered vehicles, where when we burn fossil fuels, we've seen these balanced equations before in this class. Octane, for example, if you burn it, it makes CO2, which goes into the air. Also electricity generation, largely burning coal in a lot of places still, even in North America. Natural gas, any kind of fossil fuel that's being burned, major sources of CO2. This is global emissions up to 2015. Notice, like since 1950, there's been a bit of a spike. And this is kind of broken down into the different countries that are doing the emitting. For a long time back here, Europe was the major emitter. Then the US kind of took over, kind of in here. And now the US and the EU are both decreasing. And China has come in to fill the gap. And several other countries you can see are listed there as well. Canada would fall into this America's other category, this green category in here. So question, how can we know what CO2 levels were hundreds of years ago? And we do this from taking old air samples trapped in ice and core samples. The number 2 most important gas is methane gas. They believe that methane is responsible for about 21% of this enhanced greenhouse effect, and that CO2 is responsible for like 78% or something like that. So methane gas is not as important, but it's still quite important. Methane gas comes from a lot of different sources, some natural, some human. So a major one is actually wetlands, that if you take organic material and put it in water that's not moving, what happens is it'll rot, it'll decompose, and it'll use up the oxygen in the water, and then it'll continue to decompose when the oxygen's gone via an anaerobic process. And the anaerobic process, when you have standing water, generates methane rather than carbon dioxide. And then the methane will come up from these swamps, these wetlands, and enter the atmosphere and contribute to global warming. So wetlands, I guess, are largely natural, I guess, although there's certainly human influence in these as well. If you flood an area to make a dam, for example, that'll flood a lot of land and generate more methane as well. Termites are responsible for about 20 megatons a year. In their bodies, they eat wood, which has cellulose in it. Most animals can't digest cellulose. So what termites do is I think they have symbiotic bacteria that can digest it, that live in their guts. And these produce a lot of methane gas. Cows do too, actually. See, cows are there. I think we come back to them. Atmospheric methane, we know, by the way, it's increased, it's spiked just like CO2 levels have in the last couple of years, last 100 years or so. So we know it's a result of human activity, so it's not just all these natural sources. Garbage dumps are an important source. You bury garbage, it doesn't have access to oxygen, it will decompose and produce methane as well. Rice paddies, again, it's like flooding area, making stagnant waters. Very pretty picture, but rice is usually grown in flooded fields. I used to think that rice needed a flooded field to grow. It turns out rice grows just fine in regular soil, but it also tolerates being flooded. And so the reason they grow it in these flooded areas is because it's like easy weed control. Because very few weeds can grow in flooded areas, but the rice can still grow. So it allows easy weed control. Ruminant livestock, like cows, they also eat cellulose that is broken down in their guts by bacteria, which generates a lot of methane gas. And, you know, I have this here as a human activity. And, like, these are obviously naturally alive things. But one thing I can definitely say, though, is the number of cattle on this earth right now is much, much higher than it naturally would be because humans cultivate them, you know, raise them and use them for meat and leather and milk and other things like that. So this number would be, you know, 10 times smaller than that if we didn't exist and there's only natural populations. Energy mining is an important one. This is a Spring Hill, where every once in a while methane pockets will explode underground, causing mining disasters. And there's about 100 megatons released every year due to energy mining. Waste treatment's another one. You may have seen wastewater treatment plants that look like this. They have these like settling pools, and you know, sewage goes in there, and it's allowed to basically sit and brew for a while, and this helps it get treated. Sometimes these are aerated, which would not produce much methane. Sometimes they're not. So these are another important source of waste. I had a student once, and she had a summer job working in Ottawa. There was this project where the Ottawa River has all these houses and cottages that run along it, and most of them were on septic systems that, you know, weren't connected to public utilities. And so what was going on was a lot of these septic systems were in bad repair. They would fill, and then the waste beyond that point would sort of leak out and leach into the river. And it was a project they were trying to clean up the river. So they just went from like house to house to house, checked out for free their septic systems, and then would pump their system if it was full for free. And so this is her job. She would go house to house, and they'd, these trucks, and they'd fill them up, what they pump out. And they'll go drop it off at this site like the one you see in the picture here. And it would all sit in there, and it would go through these multiple stages. The first one sits there for a while, and then it separates, and you get this sludge at the bottom, which is the solids, and you get the liquid at the top. And apparently what they did is this was next to a public park, and had these like giant water cannons, and they would like suck the water off the top at night and spray it over the whole park. And what that would do, like apparently the park grew vigorously because it was like really good at fertilizing. It had a lot of dissolved nitrogen and stuff in it. And then the sludge that's left over, the solids, it's often called biosolids. And it can be used as fertilizer too, although some people are a little bit antsy about using human-derived biosolids as fertilizer. I think a main reason is because we actually use a lot of medicine, and that medicine ends up in our sewage. And what, if any, are the effects of that on soil and food grown in that soil and so on? I think there's just some potentially unanswered questions there that people get worried about. Anyway, sounds like a fun job, I guess. I don't know. Actually, it doesn't really sound fun at all, but someone's got to do it. All right, so these are all the different estimates of different sources of methane gas. There's a lot of uncertainty in a lot of these. So, I mean, we don't have a super tight grasp on exactly what these numbers are. So every different gas has a number associated with it that we call the global warming potential. And really what the global warming potential is like, how bad is this gas for forcing climate change per molecule? And it's given carbon dioxide 1 as kind of like the ratio. So if you emit 1 molecule of CO2, what impact will that have on the environment? Now obviously 1 molecule is going to have a negligible effect. But if instead of releasing a molecule of CO2, you release a molecule of methane, methane turns out to be 25 times worse than CO2. So the effect of releasing 1, say, kilogram of methane into the environment is the same as releasing 25 kilograms of CO2. And that's because it's maybe more effective at absorbing infrared light and sending it back. And it could also be because it has a longer lifetime in the environment. That's okay. So when I say methane is responsible for about 21%, and CO2 about like 75, 78, somewhere around there, it's not because we have 3 times more CO2. It's like we have 50 times more CO2, But if you go down this list, there's some interesting entries. CFC 11, CFC 12, 10,000, 5,000. CFCs were really, really, really potent global warming gases. In addition to destroying the ozone layer, they're also terrible for global warming per molecule. Now again, you need both the global warming potential and a large enough volume of them to have any effect. There are some HFCs. Remember, those replaced the CFCs? HCFCs are here. HFC is here. These are all numbers in the thousands as well. So all of these replacements we have for CFCs are all pretty bad too. This one, sulfur hexafluoride, that's super bad. 22,800. So, there's lots of other gases that may be present in very, very, very small amounts, but the impact is outsized of these particular things, just because there's so many, there's such a high global warming potential for each one of these different molecules. All right. CH4, methane, goes by lots of names. It's sometimes called marsh gas because it's produced by marshes. Methane, natural gas is what it's also sometimes called. And propane is something it's not called. Propane is something else. Okay. So, we've identified the issue. Number 2, technological solutions. We have many that have been deployed to varying degrees. Electric cars, of course, an important one. This is kind of an old picture now. We know electric cars are starting to become run-of-the-mill, I guess maybe I'd say. I don't know, if you looked around, it's what, 5% of cars, do you think, electric now here? Other countries, it's much higher. Like, I think Norway is at like 50% electric cars already. So we're behind other parts of the world. The problem is, though, when you have electric cars, is that electricity has to be generated somehow. So if you generate that electricity by burning coal somewhere else, that doesn't necessarily solve the problem. So you need green ways of generating electricity that don't produce the fossil fuels too. So this is a solar farm outside of Disney in Florida. Florida's a great place for it because they get lots of sun. And I believe this generates, it's not the only one, they have several of these. They generate enough electricity for, I forget the percentage of the power that the parks use that is generated on their properties by these as well. I don't think it's completely self-sufficient, but I think a lot of it does get generated on site. There's other solutions now where people are trying to see if they can actually pull carbon dioxide out of the air. And this is called carbon capture technology, and there's some different companies working on this. So the idea is you take concentrations that are high in CO2, like directly out of a plant, and you somehow extract out the CO2 in a way that cleans the air. So this is being attacked, this problem, from many, many different angles. I wouldn't say there's like an easy, cheap, just put it in place technology that can replace fossil fuels just yet. So while we've made a lot of progress in that stage 2, that second step, we're not quite able to completely cut ourselves off if we want to maintain our same levels of, you know, lifestyle and production and activity and travel and so on. I remember thinking once, it was actually one of these weird thoughts, it's like, if you were going to design a product where its job was to remove carbon dioxide out of the air and replace it with oxygen or something like that, think about the features you'd want it to have. You'd want it to be cheap. You'd want it to involve zero maintenance. You'd want it to not require electricity. You'd want it to be solar powered, ideally. You'd want to be able to store the CO2 in a solid form or some form that can't just be released accidentally back. And ideally, if you could turn that CO2 into some useful product, that would be even better. And I remember, like, I was thinking about all these things you'd want to install in it. And the more I thought about it, I'm like realizing I'm just inventing a tree. Because a tree requires no maintenance. They're self-propagating. They take CO2 out of the air, turn it into a solid material, which we can use as a building material or a fuel. Solar powered. And of course, it has a whole bunch of other benefits for the ecosystem. So really, one way, I think, an important way of getting rid of carbon in the air is to make sure that we protect forests and maybe increase forest coverage that we have right now. I saw this group, it was an interesting one on the internet once, and they're like guerrilla tree planters. Not like gorilla the animal, but gorilla as in like, you know, guerrilla warfare. And what they would do is like go to like people that own lots and things like this, and they would just plant trees under the cover of night in like just empty spaces. And they just like, if 10% of them are just not noticed and grow into a full-size tree, have met their goal. They're just trying to increase the density of trees in human-occupied spaces, which is kind of an interesting approach. The next couple slides, many slides. I think this is a good time to stop, actually. All these slides are about the political side, which is sort of the last step after the technological solutions. I'm going to leave that till next week. So you guys have a wonderful weekend. Enjoy some of the sunny day today, and we'll see you all next week.